Day 10 of 90 focused on pointers fundamentals. The goal today was making pointers fundamentals safe enough that ownership and lifetime stay visible in the code. I did not want a language feature tour. I wanted a model I could still explain after the demo code grew into a real application. The first concrete check was who owns the object. That sounds small, but it decides whether the code reads like a contract or like a lucky sequence of feature choices. The second check was when the lifetime ends. That is usually where bugs start if the edge of the system is vague, because bad assumptions leak deeper into the app before anyone notices. The third check was whether the caller can mutate the value safely. Once that was visible, make ownership, lifetime, and mutation visible enough that the code explains who frees what. That is what made the lesson feel reusable instead of tied to one tutorial example. The implementation only started to feel solid once treat stack allocation, heap allocation, and move semantics as design choices instead of accidents. In C++, that usually means the types, ownership rules, and build choices all need to agree about who owns each decision. I kept returning to one more rule: use RAI and smart pointers so cleanup survives both success paths and failures. That is the part that shortens debugging because the code tells you where to look instead of forcing you to reconstruct the intent from scratch. The predictable mistakes were letting ownership stay implicit until leaks, dangling references, or double free show up and moving values around without deciding which object still owns the lifetime afterward. They look different on the surface, but both come from letting convenience win over clarity. So my recap for day 10 is simple: making pointers fundamentals safe enough that ownership and lifetime stay visible in the code. Keep who owns the object, when the lifetime ends, and whether the caller can mutate the value safely visible, and the code stays much easier to test, explain, and change. One reason I keep drilling these days is that production changes usually alter the surface area, not the core contract. If the contract is clear, the refactor stays local instead of infecting the whole project, and that is a much better place to be when release pressure shows up. That is especially true in C++, where templates, headers, allocators, and threading primitives can all make the code look more connected than it should be. Clear ownership prevents the drift and gives you a much smaller search space the first time something breaks. A lot of debugging time disappears when the request path, thread handoff, or ownership path is obvious from the structure. The language helps, but only if the design is honest and the boundary is visible in naming, types, and flow. My test is simple: could I explain this same design tomorrow with a different example and still keep the same reasoning? If yes, the lesson probably landed for real. If not, I probably memorized a recipe instead of understanding the trade-off. I also ask where the next teammate would hesitate. That question usually points at the first boundary that is still implied instead of stated, and cleaning that up early is almost always cheaper than doing it after two more features land on top of it. When the code is shaped well, the types, functions, tests, and diagnostics tell the same story. When they do not, the mismatch shows up in review before it shows up in production, which is exactly where I want the correction to happen. That is why I keep practicing with one concrete path at a time. A small path is enough to reveal whether I understand the design or only recognize the tooling around it, and that is a much better signal than just getting the sample app to run once. The pattern I am looking for is repeatability. If I can take the same boundary, reuse it in a slightly different context, and still trust the behavior, then I know the lesson moved from recognition into working engineering judgment. That is also why these daily rewrites matter. They force me to say what the code is promising, what would break that promise, and what would help another engineer recover the intent without reading my mind.